People, can you hear me? Can you hear me clearly? Yes or no? You can hear me, ne? Right. Today we will discuss the BioEve paper 22. BioEve paper 22. Find that paper. BioEve 22. I have shared that to the chat line. Share it to the chat line. Right. Let's discuss this paper. Right. People find this paper. I have shared it with the chat. So find this paper. All right. So let's find answers, people. First question. Which of the following best describes the process of diffusion in plants? Following describes the diffusion in plants. Movement of molecules. Which of the following best describes? Let me adjust this little bit. Which of the following best describes the diffusion in process? What is that, people? Diffusion, how do you describe then? Movement of molecules from less concentrated to more concentrated area. You don't need this, need. I'll close this one and I'll talk like this. Right. First one, movement of molecules from less concentrated to more concentrated. Movement of molecules from less concentrated to more concentrated. Yeah, less concentrated to more concentrated, that doesn't happen in diffusion, right, people? So it's not happening in diffusion. Then active transport of molecules using ATP. No, diffusion is not an active process either, wrong, people. Movement of molecules from more concentrated to less concentrated, that is correct. So you can take that as the answer. And then transport of water through xylem vessels. No, that's not neither. Transfer of water through xylem vessel. What is the method, people? What's the method of transport of water in the xylem vessel? What is the method? You tell me that. What is that method? Transport. Just give me 1 second. 1 second, 1 second. Right. Okay. This is more comfortable. Movement of water molecules from more concentrated to less concentrated area. That's correct. You can take that as the answer. Right. And then transport of water through xylem vessel is bulk flow. That's not the answer. Wrong, neither. And then next one, people, use of transport protein for molecule movement. Transport protein for molecule movement, you know that cell membrane does that, right? So that's not the expected answer. What's your answer, my dear? Third one, neither. Third one, very good. Question number 2. Question number 2, imbibition in plant refers to. Imbibition in plant refers to. Can you give me the answer? Imbibition is referred to. Imbibition, who's going to give the answer? Imbibition in plants refers to. We said that we will adsorption, right? Imbibition is what? Adsorption. So we say that absorption of light for photosynthesis. What's that? Neither. Wrong, neither. We can't take that. Light absorption. And then people, movement of water in xylem vessels, no. And then adsorption of water molecules by hydrophilic materials, that's the correct. Too easy to answer, ne? Too easy. And then people, active transport of nutrients, no. And then diffusion of gas through stomata, no. So we have the answer, third one for question number 2. So question number 2, right here, question number 1, answer is third. Question number 2, also answer 3. Question number 3. Now we discuss question number 3. Question 3. Question 3. Which type of transport in plants involved in transport through protein and is a passive process? What's that? Which type of transport in plants involve transport through proteins and it's a passive process? Transport through proteins, which is a passive process. What's your answer? What is your answer? Bulk flow? No. Bulk flow, of course, passive, but it doesn't flow through transport proteins. No, wrong. And then active transport. Active transport need energy, so it's not passive. Wrong. Osmosis is passive, but it does not necessarily flow through transport protein. Osmosis can take place, people, through lipid bilayer as well. It can happen through the lipid bilayer too. So it's not need to be, it's not necessary to be, passing, it's not necessary to pass through channel proteins. No. Facilitated diffusion, yes, that is the answer. Every time in facilitated diffusion, they have to flow through, uh, the transport proteins, because these membrane proteins are facilitated diffusion, yes. And then diffusion, no. Diffusion, even a membrane is not required for a diffusion. So you know the answer, third one, people, for question number 3. Answer is third. Question number 4 is the one that we discuss now. Bulk flow in plant is characterized by, bulk flow in plants is characterized by movement of substance through metabolic energy. Movement of substances using metabolic energy. Bulk flow is passive. Movement of substances from lower to higher pressure region. Low to higher pressure region, no, higher to lower pressure region. Higher to lower, neither. Wrong, that's not the answer. Movement of liquid and material in response to pressure gradient, yes, that is the right answer. And then people, movement along concentration gradient, no, that's not a bulk flow. Bulk flow is moving in large volume along a pressure difference. So movement through the phloem only, no, even bulk flow occurs through the xylem too. So I'm taking third one for question number 4. Third one, question number 5 in discussion now. Question 5. Solute potential in plant is, solute potential in plants is independent of molarity of a solution. Solute potential, what is solute potential? Decrease of water potential due to solute, right? When you dissolve something in water, it can be salt, it can be sugar. What happen? Water potential goes down. Solute potential, the negative value increases, right? The solute potential in plant is independent of the molarity of a solution, independent of the molarity of a solution, independent of the molarity of the solution, solute potential, no, it's not independent, wrong statement. Directly proportional to the molarity of the solution, yeah, more the solute, lesser, directly proportional. Then always positive value, no, always negative. And then people only affected by mineral ions, no, it can be even any other solute, not necessary to be minerals, no. The same as pressure potential, same as pressure potential, no, 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 no. So we got the answer now. Second one is my answer. Question number 6 in discussion now. Question number 6 in discussion. Question number 6, pressure potential in plant cells. Pressure potential in plant cells. Pressure potential in plant cells. So please send the paper there. I send it once. Right, next one, pressure potential in plant cells is always negative. Pressure potential in plant cells always negative. No, pressure can be negative, pressure can be zero, pressure can be positive, pressure can be any of these if variable from minus to positive in a range, it's variable. Pressure potential in plant cells always negative, no. We learn pressure potential in a living plant cell is either zero or positive. What we said? Pressure potential of living plant cell is zero or positive. In pressure potential of a live plant cell never becomes negative. Pressure potential of some of the dead plant cells like in xylem can become negative. Hope you understand these things, right? Always negative, independent of turgor pressure. Pressure potential is independent of the turgor pressure, no? You know, when water enters into a system, system expands. So it pushes the cell wall out. It pushes the cell wall out. When water enters into a system, cell wall, cytoplasm fail to expand, cytoplasm expands. It pushes the wall out. Wall applies equal and opposite force. We call this as the wall pressure. Because of the wall pressure, cytoplasm resists to expand. As a result, TP, turgor pressure, builds inside of a plant cell. Can independent of turgor pressure? No. So what happened, people, when the turgor pressure builds up, pressure rises. As a result, psi P rises. That's how it happens. That is how it happens. And then so is not affected by osmotic, always positive, not affected by osmotic uptake of water, wrong, affected by, only occurs in xylem cells, turgor pressure, no, not only in xylem. Xylem, it can be present in people, any living plant cell, the positive turgidity can be built up. So I have the answer. Pressure potential of a plant cell can be positive, negative, or relative to atmospheric pressure. That's correct, Nick. So shall we take the answer as third one, people, for that question? We are now discussing question number 7. Question number 7, my dear. Question 7. How does movement of free water molecule, how does movement of free water molecule How does movement of free water molecules occur across selectively permeable membrane in osmosis, and what is the direction? You understand that? How does the movement of free water molecules occur across the selectively permeable membrane in osmosis? Now, osmosis, water can go through the lipid bilayer as well as they can pass through channel proteins. From lower to higher concentration of free water molecules. Yeah, osmosis is movement of free water molecules. I agree with you. From higher to lower concentration of free water molecules. Low to higher, wrong, ne? Higher to lower water concentration. From higher water to lesser water direction, water moves. Second is okay. Independent of the concentration of water molecule. Independent of the concentration of water molecules doesn't make much sense. From lower to from lower to higher concentration of solutes, from lower to higher concentration of solutes. Not wrong, but that's not the definition neither. And then from the area of high pressure to low pressure, from the area of high pressure to low pressure, no, that's a bulk flow. So we'll take people's second one as the answer for question number 7. Question number 8 in discussion now. Question number 8, water potential is the difference between solute potential and the pressure potential. Water potential is the difference between solute potential and pressure potential. No, water potential is the ability of water to move. It's something related with the energy present in water. It's a difference between solute potential and pressure potential. Solute potential and pressure potential difference. It's the total, neither. It's the total of water potential and the solute potential. If you say total, better. But anyway, 0 or negative water potential, it can be positive too, and occurs due to movement of water through membrane. Occurs due to movement of water through membrane. Occurs due to movement of water through membrane. Water potential. No need to have a membrane for that, ne? No. Determines the direction of water movement between cells, that's correct. And then defined as 1 megapascal for pure water without applying any pressure. No, neither. Wrong. Ne? So we have the answer, people. Fourth one is the answer. Ninth question. How does pressure potential function within cells? How does pressure potential function within cells? Right? I'm just giving you a small help. I know that you can answer these questions. I know you have answered these questions. Otherwise, you won't join for this meeting either. People who have answered only join this meeting, and then those who fail to answer, people, they don't even think about joining of BioEve. Ne? So congratulations, you are ahead compared to the others in the batch. So that's something that you have to be neither happy about yourself, right? So you're in right track, people, right path. You're at the moment managing your work, and then you have taken responsibilities. Probably your parents doesn't know that you have a class right now, neither. So that it's just a last moment, a small message, neither sent to the group. You simply can neglect it, but still you have taken the responsibility to join with the meeting. Congratulations, right? You are in right track. Just maintain it. This will take you to the required task, target, required level in your life. You have committed yourself in studying. Very good. Superb, right? So we don't have like put extra force for the other people to join, right? This is enough, ne? This number is enough. So continue your work, right? So happy about you. I'm proud about you, really, right? I'm really telling that truth. I'm really proud about you all, people. Right, question number 9. How does pressure potential function within cells? My letter size is too small, ne? I think I should print it little bigger, ne? I'll do that next time. How does pressure potential function within cells? Pressure potential is always positive. increasing the water potential of the cell and is independent of the atmospheric pressure. Pressure potential is always positive. You can't say that, ne? Sometimes some tissues, like in xylem, pressure potential can become even negative, right? Pressure potential is always positive. No, increase the water potential of the cell and independent of the atmospheric pressure. So it's wrong, ne? First statement is not valid. It fluctuates between positive and negative values, impacting the water potential based on the cell turgor pressure. Fluctuates between positive and negative values, correct. Impacting water potential based on the cell's turgor pressure. Yeah, water potential, pressure potential can become positive, negative. So it affecting for the cell turgor pressure. Yeah, that's correct. Pressure potential remains constant in plant cells. No, wrong, neither. And then it's always negative, decreasing water potential of the cell and is influenced by external atmospheric condition. Always negative, no, we don't agree with that. Pressure potential is determined solely by the osmotic potential of the cell and does not affect water potential. No, wrong, neither. It's affecting water potential of the cell. So we can go with the second as the answer. Question number 10 in discussion, moving to next page. People turn to next page. Turn to next page. Right. How does concentration of mineral ions in the root hairs compared to that of the soil solution, and what does it imply about the mechanism of mineral ion transport in these cells? Right. Need little help here. How I look like with this? Now it's clear for me. Right. So let's go with that. How does concentration, these letters are too small for me to read. How does concentration of mineral ions in the root hairs compare to that of the soil solution? And what does this imply about mechanism of mineral ion transport in these cells? What he says, how does the concentration of mineral ions in the root hair compare to that in the soil solution? What do you know about mineral ions in the root hair cells are always higher than the mineral ion concentration present in the soil solution. The concentration of mineral ion is lower in root hairs, wrong. The mineral ion concentration is same in both root hairs, no. The concentration of mineral ion significantly higher, yes, that's correct. That is correct. Mineral ions are not absorbed by root hairs, but no, absorbed. The concentration of mineral ions in the root hairs fluctuates unpredictably, no. Fluctuates concentration, no. It actually moves by active transportation. So we'll take third one as the answer. 10th question third. 10th question third. 11th question in discussion right now. 11th one. In absorption of water and minerals from soil, how does structure and the functionality of the root hairs optimize? In absorption of water and minerals from the soil, how does structure and the functionality of the root hairs optimize this process, and what implications does this have to overall efficiency of nutrition uptake and water absorption? Long questions, neither. In absorption of water and minerals from the soil, how does structure and the function of the root hairs optimize it? So what features present in root hairs to enhance the absorption of minerals and water? Root hairs are primarily structural and do not significantly contribute to the water and mineral absorption. No, root hairs contribute for that. They decrease the efficiency of nutrition uptake due to their limited surface area. What they say? They decreases the efficiency of nutrition uptake due to their limited surface area. The absorption of water and minerals from the soil. How does the structure and the functionality of the root hairs optimize? Root hairs increases the surface area for absorption, enhancing efficiency of water and mineral uptake from soil. Crucial for the plant nutrition. That's correct. The third one is the answer. 11th, third. You agree with me? 11th, third. The main function of the root hair, the fourth choice, is to anchor now. And then root hairs absorb nutrients and water through active. It can be active or passive. So I'm taking the answer here, my dear. Let's take the answer. Third one. Third is the answer for 11th. Third is the answer. Question number 12. Cell X and Y are two adjacent plant cells. Cell X and Y are two adjacent plant cells. The water potential and the solute potential values of these cells are as follows. Okay, we have to write that. Let's write that. So we have two cells, X and Y. Two cells, X and Y. Cell X, water potential. This is X. This is Y. Cell X, water potential. Psi is minus 0.7 megapascal. And then psi S of that is minus 1.0 megapascal. So you can find the water potential, pressure potential here. Psi is equal psi S plus psi P. Psi is minus 0.7. Psi S is 1.0 plus psi P. So we can get psi P value. Psi P value is 0.3. Psi P value 0.3. Right? And then cell Y, psi is equal to minus 0.5 megapascal. Psi S is equal to minus 0.8 megapascal. So you can find psi is equal psi S plus psi P. So you can find the pressure potential once again. This is minus 0.5 plus is equal minus 0.8 plus psi P. So you can get psi P value as 0.3. Once again, same value, 0.3. So what they say, which of the following statement is incorrect? Water will move from cell Y to cell X. Now, transport of water is affected by the water potential difference. Now, which cell has more water potential? This cell water potential is minus 0.7. This one is minus 0.5. So, from higher to lesser, out of X and Y, Y cell is having higher water potential. X cell has lesser. So, it move from Y to X direction. Water is going to move. Water moves from Y to X direction. Right? That direction, water is going to move. Water will move from Y to X. That's correct. Movement of water will continue until the water potential of both cells become equal. Correct. Psi P of the cell X is 0.3. Yes. Psi P of the cell Y is 0.3 megapascal. Correct. The water potential and the solute potential values of normal plant cell can be positive or negative. Water potential values and the psi S. No, psi S is always negative or 0 in pure water. Otherwise, people, it never becomes positive. Answer is 5. Question number 12, I'm taking answer 5. Question number 13. Question 13, my dear. Question number 13. Two samples of upper epidermal tissue from Tradescantia leaf were placed in two different sucrose solutions labeled as C and D. Okay, let me erase this. Let me erase this one. So they say two samples of upper epidermis tissue of Tradescantia, different sucrose solution C and D. So one sucrose solution is C, this is C sucrose solution. The other one is D sucrose solution. The other one is D solution, D sucrose solution. Two samples of upper epidermal tissues of Tradescantia immersed in two different sucrose solution. So it's the same epidermal tissues. Some of them you immerse here. Since it's the same tissue, they have the same solute potential values. The tissue has the same solute potential values. Based on the percentage plasmolysis, right? Based on the percentage plasmolysis, you can find out, based on the percentage plasmolysis, you can find out the solution, right? That is isotonic. So, 50% plasmolysis occur in isotonic solution. So, the solute potential of cell C, psi S of this solution, minus 2000 kilopascal. And that of the solute D, psi S of the solution D is minus 1600 kilopascal. Harida, upon reaching the equilibrium, it was observed that 50% of the cells in the tissue immersed in solution C were plasmolyzed. 50% plasmolysis here. 50% plasmolysis in solution C. Then you know this relationship. What is that, people? Solute potential, water potential of the outer solution, water potential of the solution C solution is equal to, solution C is equal to solute potential of solution C is equal to water potential of this cell, water potential of the cell is equal to solute potential of the cell. So these solute potential value they have given as 2000 minus. So now you know solute potential of the cell. You know solute potential of the outer solution. Now you know solute potential of the cell. You know solute potential of the cell. Right? You learn that theory part. Haridhar. So you know the solute potential of the cell. Solute potential of the cell is now minus 2000. Don't ask why. You learn the theory part. So you know these solute potentials. Solute potential of these cells are also 2000 minus. It's the same tissue immersed here. So solute potential of this one is also minus 2000 kilopascal. You know the solute potential of these cells now. And you know outer solution water potential value. At equilibrium, what do you know? At equilibrium, you know water potential of the outer solution is equal to water potential of the cell, and that is equal to solute potential of the cell plus psi p of the cell. Psi p of the cell. This one is minus 1600. This one is also minus 1600. Cell value is same, ne? So the solute potential value is minus 2000. And psi p you have to find. So psi p, you can now find psi p of the cell. You bring this 2000 this side, it become plus 2000. So plus 2000 minus 1600 is 400 kilopascals. 400 kilopascals. Right? It's 400 kilopascals. Is it okay, people? Is it okay? Did you understand that? Right? Any problem with that? All right. So what they ask now, okay, they have given some statements. We have to check the validity. We have to check the validity. Any problem, my dear people? Any problem? So what is status Cantial? Royo. Right? Royo. So here, water will move from water on here. So the answer for 13th question, 13th question answer is then people 4. Question number 14. Question number 14. Question 14. A plant cell having solar potential of minus 2.2. So I have to erase this. It is okay. This is simple calculation, right? They have given this as 2000. 50% plasmolysis occur means the cell solar potential value of the cell is 2000. So you know that, you know this. Solar potential value, psi s value of the cell. And outer solution water potential is a cell water potential. Outer solution water potential is a cell water potential. So that's 1600. Solar potential is 2000. So you have to find pressure. Simple, eh? You have to find pressure. Simple task. Right, moving to next question. Moving to next question. Moving to next question. Question number 14, a plant cell having a solar potential, minus 2.2 megapascal and pressure potential of 0.5 was placed in a sucrose solution of minus 1.8 megapascal for 45 minutes. Which of the following is correct? Right, we'll take this. What they say, a plant cell having a solar potential, plant cell having psi s value minus 2.2 megapascal, pressure potential psi p 0.5 megapascal, placed in sucrose solution. This solution with solar potential, outer solution, solar potential minus 1.8 megapascal for 45 minutes. Now, outer solution, solar potential is given. People, outer solution pressure is 0. This sort of solution pressure we take people as 0 because there is no extra pressure, right? So outer solution solar potential plus outer solution pressure is equal to its water potential. So this one is minus 1.8. This is 0 plus 0. So that the outer solution water potential is minus 1.8. Minus 1.8. So this is minus 1.8. Minus 1.8. 1.8 minus. At equilibrium, this is equal to water potential of the cell. Water potential of the cell is equal to Solute potential of the cell plus pressure potential of the cell. This is 1.8. This value is minus 2.2. They ask now. What they ask? Okay, so outer solution is this much. We'll outer solution, now we find the value in the outer solution. Okay. We learned that this outer solution, water potential of the outer solution is minus 1.8. Hurry. Let's take the cell values once again. Cell psi S of the cell is minus 2.2. Pressure potential of the cell, psi P, pressure potential of the cell is plus 0.5. 0.5. So what is the water potential of this cell? We know after 45 minutes, the cell has to come to this value. But what is the water potential? How do you find that? Water potential is equal psi S plus psi P. So minus 2.2 plus 0.5 kileno. So value minus 1.7 kileno. So cell water potential is minus 1.7. Outer solution water potential is minus 1.8. So who has more water potential? Right? Cell has more water. So that the water tend to flow out. Water tend to flow out from the cell. What do you call that sort of a flow? Exoosmosis. Exoosmosis. Check that. Which of the following statement is correct? The cell is, when the cell is in equilibrium, the water potential is equal to the pressure potential. No. When the cell comes to the equilibrium, outer solution water potential and the cell water potential become equal. That's all. So first statement wrong. The new pressure potential is lower than the initial pressure potential. Water comes out. So what is initial pressure? 0.5. As water comes out, the pressure has to decrease. So it says the new pressure potential is lower than the initial. That is correct. 14th second is correct. Anyway, we'll check the other statements too. The cell goes into incipient plasmolysis. I don't think that will happen. Cell pressure will not come to 0. Right? So if you want, you can calculate it. What is the final water potential? Final water potential is this value. So you can apply, you can check this pressure, unknown pressure. Right? You can find out the equilibrium. You can find out equilibrium pressure potential. Right? You know, at equilibrium, cell water potential become the outer solution value. Now, previously we calculated it before reaching to equilibrium. So when water move out at one point, when water move out at one point, water potential of the cell, psi S plus psi P at equilibrium. Check this, at equilibrium, outer solution water potential is a cell water potential. So minus 1.8 is a cell water potential. Cell solute potential is going to same, not going to change. New pressure potential you have to find. So you can find that pressure potential, psi P value. This goes this side, become positive. So 0.4 megapascal is a new pressure value. Previously it was 0.5. Now it has dropped down to 0.4. So this statement is valid. Second statement is correct. The cell goes into incipient plasmolysis. That is wrong. If the cell goes to incipient plasmolysis, what should happen to the cell pressure? Cell pressure has to come to 0. It's not coming to 0. It stops at 0.4. So wrong. Fourth statement, there will be no exchange of solute in between the cell and the solution. That is correct. There is no exchange of the solute between the cell and the outer solution. There will be no exchange of solute between. That is correct. Fourth one is okay. Fourth one is also an answer. If they want us to select the correct statement. The solution of solute potential minus 1.8 megapascal is an isotonic solution. No. You know, outer solution water potential is minus 1.8. 1.8 compared to the cell. Cell water potential is minus 1.7 at the beginning. So compared to that, outer solution is hypertonic. That is why water comes out. Hypertonic solution. Wrong. So we have two answers. Second and we can take fourth as the answer here. So question number 14, second and fourth. Two answers I got. Next one. Question number 15. Right, I'll erase this. Question number 15. Question number 15. Question 15. All right, people, let's check that. Question 15. Plant cell with solute potential minus 1.5 and pressure potential of 0.3 is placed in sodium chloride solution with solute potential of minus 1.2 megapascal for 30 minutes. Which of the following statement is correct? Right, we'll check that. What it says, plant cell with solute potential, plant cell with solute potential psi s. What's the value? Minus 1.5. Pressure potential psi p. Key the value become 0.3. So what is the water potential here? Water potential is equal psi s plus psi p. So water potential you can calculate minus 1.5 plus 0.3 kila kiyanne minus 1.2. Right? This is immersed in a solution with a solute potential. Outer solution solute potential value is minus 1.2. You know, based on this you can find water potential. Based on this you can find water potential. Water potential is equal psi s plus psi p. Psi s is minus 1.2. Psi p is 0. Psi p is 0. Therefore, water potential is equal minus 1.2. Minus 1.2. Harida. So, this outer solution water potential is also minus 1.2. Cell water potential is minus 1.2. So, compared to the cell outer solution and the cell water potential equal. That means cell is in isotonic solution. Cell is in isotonic solution. Let's answer the statements now. Water potential inside the cell is equal to the pressure potential. That is wrong. Neither. Water potential inside the cell is equal to pressure potential. No. Pressure potential is 0.3. Ne? Wrong. The new pressure potential is higher than the initial pressure potential. No. I mean, there is no water loss. So the pressure potential won't change even after 30 minutes. The cell undergoes fully plasmolysis. No. Cell is not going to change because the water potential inside outside of the cells are equal. And then there is a continuous exchange of solute between the cell and the solution. No exchange. Wrong. The sodium chloride solution of solute potential 1.2 megapascal is isotonic. That is correct. So we'll take that, people. 15th one. 5th one is the answer. Last question. MCQ 16th. Last question 16th. Right? Shall we check that also? What did you get as the answer for that, Lamai? Question number 16. What is your answer? Can someone send me the answer? Who's going to send me the answer for question number 16? Question number 16. Who's going to send me the answer? Anyone? Who's going to send me the answer? Ko Lamai. Send me the answer. Okay, 5 blue. 5. One student give the answer. How about the others? How about the others? 16th question. 16th question. Let's begin that. What it says. Read that. Two potato strips in same diameter, 5 centimeter long, were immersed in two sucrose solutions named A and B with solo potential minus 1500 kilopascals, minus 2030. Okay, we'll check that. Two potato strips, 5 centimeter, two potato strips of 5 centimeter, immersed in two sucrose solutions named A and B, which in which solo potential were minus 1500 kilopascals, in which here solo potential of the solution is minus 1500, and here the solo potential of the solution is minus 1230 kilopascals. After equilibrium, the length had become 5.2 centimeters only in the strip immersed in A. So this is 5 centimeter at the beginning. At the end, it becomes 5.2. It becomes 5.2. Which of the following is not acceptable regarding A and B solutions? Not acceptable regarding A and B solutions. Solution A is relatively hypotonic. Now look at this. Length increases, ne? Hypotonic, correct. Otherwise, length cannot increase. They are asking not acceptable. So first statement correct. Water potential of the tissue immersed in solution B is equal to minus 230 kilopascal. Water potential of tissue immersed. Only in the strip immersed in solution A. Now they say only in the strip immersed in solution A become 5.2. They haven't mentioned what happened with the solution B. After the equilibrium, the length had become 5.2 only in the strip immersed in A solution. So you can assume that in B solution that there is no change. Ne? Which of the following is not acceptable? Water potential of the tissue immersed in solution B is equal. Maybe. We don't know, but it's possible. Water has been entered to the tissue A. Correct. The water potential of tissue A has increased. Yeah, water comes in, water potential rises. Correct. There is no entering or removing of water to tissue B. We don't know that for sure. We don't know that for sure. They haven't mentioned what happens to the final length there. So I'll take fifth one as the answer here. 16th 5. 16th 5. How many of you got 16 out of 16? How many of you got 16 out of 16? Anyone to get them all correct? Anyone to get them all correct? No? No? Right, moving to structured part, my dear people. Moving to structured part. So there are a couple of questions. Only 3 questions, A, B, C. So we'll try to answer them quickly. Let's answer them quickly. Let me wipe out this part. Let's wipe that and quickly deal with these remaining 3 questions. The following diagram represents the water potential value of 2 adjacent cells in a plant tissue. Hari. two adjacent cells in a plant tissue. One says cell X, the other one is cell Y. Cell X, solute potential of cell X is minus 1200. Psi P is 400. So you can find water potential is the total of these two. That means minus 800. The other one, cell Y, psi S is minus 1500. Psi P is 400. And then psi is equal minus 1100. What is the direction of water flow between these cells? What is the direction of water flow between these cells? This one is having low water potential. This is higher. So the movement of the water flow is on this direction, higher to lesser direction. So from X to Y, what is the water potential of each cell after reaching equilibrium? How do you find that? Add these two values and divide by 2. Water potential at the equilibrium is equal minus 800 plus minus 1100, right? And then add them and divide by 2. Minus 1900 divide by 2 කියලා කියන්නේ කීයද? කීයද? 950 නේද? Minus 950, you have to take the unit. What is the unit? Kilopascal. What is the water potential at the cell at the equilibrium? What is the solute potential value? Equilibrium for each cell, right? Solute potential value is not going to change before and after equilibrium. It's going to be same. So cell A solute potential 1200, cell B solute potential 1500. Okay. What is the pressure potential of values of equilibrium? Right. To do that, now you know the equilibrium water potential that you have to apply. Now you know this is not going to change. So psi is equal psi S plus psi P. So you know this equilibrium water potential minus 950. Solute potential minus 1500. Psi P is the new pressure potential value. We can calculate that. You can calculate that value. Now, equilibrium water potential, you know. Solute potential unchanged. So you have to calculate now psi P. So, 550 kilopascals. Here. Same like that. Since you know the equilibrium water potential, you can apply it here. You can apply that here. Minus 950 is equal psi S minus 1200 plus psi P. So this is plus 1200. Psi P value here. 250 kilopascals. So this cell X, this final pressure value is 250 kilopascals. Done. Are you ready? Sharia. And we go with the second question now. Let's see whether you got this answer, Lamai. Harida, you got this? Right? This is easy question. How many of you got this answer? How many of you received this answer? Shall we go for question B now? Haridalamai, please send a message. Is this okay? Can I erase the board? Right. Okay. You got the answer? Yep, Lou. That's good. Yep. Nice. At least there is one student to say yep. Yep, good. Right, we'll move to next question B. Consider turgid plant cell placed in hypertonic solution Consider a turgid plant cell placed in hypertonic solution with the following initial condition. Right, we'll take the solution like this. Let's take the solution like that. Turgid plant cell is placed in hypertonic solution. Turgid cell. Right. So we have the cell. This is the cell before immersing. Initial solute potential of the cell psi s. Kilamai minus 800. Psi p. Initial pressure potential 500. So what is the water potential here? Total of these two, that is minus 300. Then the solute potential of the solution, psi s is minus 1200. Calculate the initial water potential of the cell. Okay, done. Kilopascal, kPa. Next one, assume that the cell reaches equilibrium with the outer solution. Calculate the water potential of the cell at the equilibrium. Now you drop it here. Now this reaches to an equilibrium, osmotic equilibrium. What do you know, people? This is outer solution solute potential. What is the outer solution water potential? Minus 1200, because there is no pressure. So what is the cell water potential at the equilibrium? Minus 1200. What is the cell solute potential? Minus 800. Now you have to find cell pressure, new pressure at equilibrium. So you can subject that and find it. Pressure here, this become positive. You get now a negative value. You get a negative value, poor. This is now becoming minus 400. Minus 400. You know, minus values can't exist. It has to be 0 then. It has to be 0. You know, minus pressure values don't exist. Right? The minimum pressure that a plant can have, live plant cell can have, is 0. Right? So what is the change of the water potential of the solution at the equilibrium? Solution water potential does not change. You're right there. Calculate the water potential of the cell at the equilibrium. We calculate that 1200 is the answer. Then third one, what is the change of the water potential of the solution at the equilibrium? No change. And then calculate the pressure potential of the cell at the equilibrium. Pressure potential of the cell at the equilibrium is this much. Calculated, right? So here, part 1, what they ask, calculate the initial water potential minus 300 kilopascals. Part 2, assume that the cell reaches equilibrium, calculate the water potential of the cell at the equilibrium. Water potential of the cell at equilibrium is minus 1200 kilopascals. Third one, the answer has to be what is the change of the water potential of the solution at the equilibrium? What is the change of the water potential? No change. No change. Outer solution water potential is going to retain, people, at minus 1200. No change for that. Then fourth one, calculate the pressure potential of the cell at the equilibrium. Minus 400, right? Minus 400 kilopascals. But no minus values. So it has to be 0 megapascal. 0 megapascal. Hurry. 0 megapascal. Right, now we come to the last part. Part C. I think this is clear, my students. Haridalamai? Done? Is this clear? Right. Okay, Nether. Clear, ne? Harinetha, can I erase the board now? Yes, Flu. Hurry. So I'm just helping you to revise these things, people. So these BioEve and other papers, we just do them and study and do them. Ne? So that will help you to stay updated and help you to revise through the sections. That is the whole aim of taking people. The midweek lesson, a short about 1 hour discussion is taken for that, right? To keep you at the required level. Otherwise, you forget them too fast. And then people, it's very difficult later, right? To revise the sections. And that makes you really weak. So I don't want that to happen. That is why we take small discussions. Ne? This is not a big stress. Neither. And then we go to part C now. Part C. So some values given. There is a table. Neither. There is a table given. There is a table given. We have to copy that table. How many rows? 1, 2, 3, 4, 5, 6. 6 columns. Ne? 6 columns are there. 6 columns present. And how many rows, people? 3 rows. 1, 2, 3. 3 rows present. 3 rows present. Sucrose solution molarity. Molarity of the sucrose solution. Initial length. Initial. Make what lamai? Final. Final length. It was say initial length, final length. Final length in strip 1. Final length in strip 2. And then mean final length. Like a mean percentage change in length. This is 0.2, 0.3, 0.4. Right? Initial length 5.1, 5.0, 4.9. Final length 5.4, 5.3, 4.7, 4.8. Betul namai 4.9, 4.9, 3.9, 40, 3.940. Right? So you have to find now, people. You have to find now mean. You know initial length. The two strips, both strips initial length is 5.1. First one final length is 5.4. Second one is 5.3. Right? Let me take this one. This is a strip 5.1. Right? 5.1, 5.1, 2 potato strips. Final, one of the potato strips become 5.4. The other one becomes, Kilamai? 5.3, ne? This is 5.3. Let's take it as like this. There are 2 strips used in this experiment. Both 5.1 at the beginning. 5.1 at the beginning. This is final. So what is the change in length here? Can someone tell me change in length? 0.3. What is the change in length here? 0.2. Neither. So how do you get the mean change in length? Add these two and divide by 2. That you get the mean value. Ne? So how do you get that? This is these two 0.5. Ne? 0.5 divided by 2 ke lage 0.25. So mean change in length is 0.25. Is 0.25. Right? 0.25. Then how do you calculate the mean percentage change in length? This is the mean change in length. Mean percentage change in length means the initial value, sorry, mean value divided by initial. What is initial? 5.1 multiplied by 100. How do you calculate the mean percentage change? You take the change in length, mean change in length, divided by initial and multiply by 100. Right? When you do that, you get value of +5 here. +5 value. You get +5 value here. Calculate and see, okay? For the second one, it's again the same calculation. Ne? Initial value is 5.0. This one is also 5.0. What is the final values? Final value 4.7, 4.8. 4.7, 4.8. Then what is the change in length here? 5 to 4.7 minus 0.3. How about this one? Minus 0.2. So what is the change in length? Minus 5 divided by 2. Can a minus 0.25. Minus 0.25. So this is minus 0.25. So how do you find the mean percentage change in length? You know the equation is mean percentage change in length is the mean change in length divided by initial into 100. Okay? So this is minus 0.25 divided by 5.0. 5.0 into 100. When you do that, you get a value minus 5. Minus 5. Then this one, third calculation. Third calculation. Right? How do you do that? Simple, simple. You learn all this, huh? Here people initial is 4.9. This one is also 4.9. This one is 3.9. This one is 40, 40. So what is the change in length here? 1. Plus or minus, minus 1. Here what is the change in length? Minus 0.9. So what is this whole total here? Minus 1.9 divided by 2. Here the 0.95 neither. Minus 0.95. So when you apply that, this is minus 0.95. So minus 0.95 divided by 4.9. 4.9 into 100. So what do you get there? What do you get there? 19. Minus 19 loop. Minus 19. Right? Now you have to plot the graph. Now you have to plot the graph. How do you plot the graph? Mean percentage change in length versus concentration. So you can draw the graph now. This is the graph. This side is concentration. 0.2, 0.2, 0.4, 0.3, 0.1. This side, plus 5, minus 5, 19. Plus 5, minus 5, minus 19. So what is the value? 0.2 plus 5. We'll take this little up. I'll calibrate this once again. Plus 5, 0, minus 5, 10, 15, 20, ne? 10, 15, 20. Somewhere here 20. So here I have 0.1, 0.2, 0.3, 0.4. So what do you take? 0.1 kidala value veka? 0.2 kidala value veka plus 5. Somewhere here. Then 0.3 kida value veka? 0.3 minus 5. Somewhere here. 0.4 you can take minus 19. So you draw the graph. Then you plot the graph. Like that. Plot the graph. Ne? So what do you have to find now? Isotonic solution. Find the water potential of the tissue. This is the point with intersect. So I'll take this as 0.25 m is the concentration of isotonic solution. Is the concentration of isotonic solution. That's enough. Ne? That's the concentration of isotonic solution. And using a table, you can convert this into water potential. Ne? This value, using a table, convert to water potential value. That's enough for the day. We took more than 1 hour today. Unusual. So then, thank you very much. I'll see you all soon.